Good evening, all of you. So, we have so far dealt with the topics of CTFT that mainly included the basic properties, the basic theory, how to find CTFT, how to find inverse CTFT, and some of the basic CTFT transform pairs. In the next section, we are going to the next module, that is module 4 of KTU Signals and Systems syllabus. In this class, we'll be mainly dealing with how we are going to do the analysis of an LTI system using Fourier transform, that is using CTFT. What is the concept of a transfer function? What is frequency response? And what is magnitude and phase response? So let's directly move to the theory portion. That is how we can analyze an LTI system using the Fourier transform. So far, we have dealt with the continuous time Fourier transform. So we know that a continuous time LTI system is usually described by the differential equation of the form sigma k is equal to 0 to n ak d raised to k y of t by dt raised to k is equal to sigma k is equal to 0 to m bk d raised to k x of t by dt raised to k. This is the differential equation that is usually used to represent a continuous time LTI system. We know that if it is a discrete time LTI system, we used to represent it by using a difference equation. So the difference is really clear. For continuous, we use the differential, and for discrete, we use the difference equation that consists of the difference terms. Here you have got the differential term, that is the derivative terms. So in order to solve this kind of an equation, this will be the form of question that you will be having. That is, you will be given a system of this form and how you have to solve it. That is what we are going to see. We'll first take the Fourier transform on both the sides of this equation, that is on LHS as well as on RHS. We'll take the Fourier transform, that is CTFT, and we'll apply the linearity and differentiation property. On applying the linearity and differentiation property, we get a system transfer function which is of the form h of omega is equal to y of omega by x of omega is equal to sigma k is equal to 0 to m bk j omega raised to k by sigma k is equal to 0 to n ak j omega raised to k. This is obtained just by rearranging this equation. That is, this is the y of t. We'll take its Fourier transform, that will be y of omega terms. And this is x of t. On taking the Fourier transform, we'll get the x of omega terms. Y of omega by x of omega means this particular portion by this particular portion. That is, in the numerator section, you will have the bk term, and in the denominator section, you will have the ak term. That is what you have got here, and this is obtained by applying the linearity and differentiation property. So this is h of omega, which is equal to y of omega by x of omega. We know it is somewhat equivalent to the gain that you have studied, that is system output by system input. Same way, y of omega is the Fourier transform representation of the system output y of t, and x of omega is the Fourier transform representation of the system input x of t. So this is also being referred to as h of omega, may be also referred to as a frequency response of the system. Usually, this transfer function term is being used mainly for Laplace transform. For Fourier, we usually use the term frequency response to represent this particular term h of omega. Okay, so that is your y of omega by x of omega, and that will be of this form. Okay, now we need to see what is impulse response. We know that impulse response is the response of the system when the given input is an impulse function. That is, if suppose you are giving the input to the system x of t as delta of t. Delta of t is nothing but the impulse function. So if you are giving the input to the system as delta of t, what you get at the output, that is represented by x of omega. That is, the output, if you are applying an impulse function, is x of omega. You know that the CTFT of delta of t is 1. Okay, so that is what is being seen here, and y of omega will be of the form h of omega, because we know that h of omega is equal to y of omega by x of omega. X of omega value is equal to 1, hence h of omega will be equal to y of omega. So if suppose you want to find out the impulse response, what you have to find out is, you have to just find out h of omega is equal to y of omega, and we'll just take the inverse Fourier transform of h of omega. That will yield you the h of t, which is called the impulse response of the system. So this is also another type of problem that might come in this section, that is to find the impulse response. So just equate y of omega and h of omega so that you can take its inverse and you will get h of t, which is the impulse response of the system. In general, we can represent this h of omega as a combination of two terms, mod h of omega into e raised to j angle h of omega, where mod h of omega is called the magnitude part, and this section, that is angle h of omega, it is called the phase part. So on plotting this mod h of omega versus omega, we get a portion which is called as plot of mod x of omega versus omega, or mod h of omega versus omega, that is called as the magnitude spectrum or the magnitude response, and plot of angle x of omega versus omega, that is called the phase spectrum. So in order to find out mod x of omega, that is the if you want to find out mod x of omega, if suppose x of omega is a complex valued function, till now we have just said it is h of omega, whether it be h of omega or x of omega, we are just generalizing it by the term x of omega. Then we can say if it is a complex valued function of the form x of omega is equal to real part plus j imaginary part, then magnitude is root of real part square plus imaginary part square. And the phase of x of omega is angle x of omega is equal to tan inverse of xi of omega by xr of omega. We know that it is tan inverse of b by a, where b is xi of omega and a is xr of omega. Okay. And its plot is plot versus omega, it's called magnitude spectrum, and angle x of omega versus omega plot is called as the phase spectrum of the given system. Okay. So that are the main points. What is the concept of impulse response, what is magnitude response, and what is the phase response, and how to plot the magnitude as well as the phase response. Now let's move on to the first problem. Okay. So here the first problem is, consider an LTI system with the differential equation d square y of t by dt square plus 4 dy of t by dt plus 3 y of t is equal to dx of t by dt z plus 2 into x of t. Actually here by dt is also here, that is being missed out over here. So by dt plus 2 into x of t. Find the frequency response and impulse response. So we know that frequency response and impulse response, it can be found out as we have dealt in the theory section. So we are given with the LTI system like this, that is d square y of t plus 4 into dy of t by dt plus 3y of t is equal to dx of t by dt plus 2 into x of t. So we'll start the problem like this, that is we know the time differentiation property of Ctft. It is given as d raised to n x of t by dt raised to n in the time domain yields you the frequency domain representation of the Ctft as j omega raised to n x of j omega. That is, for example, if this is d square, suppose n is 2, then this will be of this form. D raised to n, d raised to 2 x of t by dt raised to 2 means that will be j omega square x of omega, x of j omega. So we'll just convert this whole equation by using this time differentiation property. So that can be converted like this. That is, taking Fourier transform on both the sides, we'll get j omega square plus 4 into j omega plus 3 whole into y of j omega, because here the common term is y of t. In all these three terms there is y of t, whose Fourier transform is y of j omega, and here it is d square by dt square, so it comes j omega square, because j omega raised to n means here n's value is 2, and the next case n's value is 1, so this is 4 into j omega, and this is just 3 into y of j omega, that will come. And here it will be what, j omega raised to 1 into x of omega plus 2 into x of omega. So x of omega will take in the RHS outside. So this will be of this form, j omega square plus 4 into j omega plus 3 whole into y of j omega is equal to j omega plus 2 into x of j omega. We need to find out the impulse response. That's first we need to find out the frequency response, h of j omega. H of j omega is nothing but y of j omega by x of j omega. On rearranging this equation, we'll take y of j omega by x of j omega. We'll take this x of j omega here, so that you can take this term to the denominator of this RHS, so that it will become h of j omega is equal to j omega plus 2 by j omega square plus 4j omega plus 3. Now, next step what we are doing, we are going to split the denominator term into its factors. That is j omega square plus 4j omega plus 3 is being split into j omega plus 1 into j omega plus 3. So this is your h of j omega. We have computed the h of j omega. Now we are asked to find out the magnitude as well as the phase part. So magnitude is nothing but we'll just take the square root of the square of the real and imaginary part. That is here. This one is omega square plus 2 by omega square plus 9 into omega square plus 1. This is actually omega square plus 4 should come. This is omega square plus 4. By mistake it has been written as 2. So please correct it as omega square plus 4. And the phase is nothing but angle h of omega is equal to tan inverse of omega by 2. Omega means it is the b part here. Omega by 2 minus tan inverse of this section, it is omega by 1. That is omega minus tan inverse of omega by 3. That is your phase part. Okay. So that is about the magnitude and the phase vector. Now we are asked to find out the impulse response. Impulse response means it is the response of the system when x of t is equal to delta of t. That is x of j omega is equal to 1. X of t, if it is equal to delta of t, then x of j omega is equal to 1. Then y of j omega is equal to h of j omega. That is what we have already seen, because h of j omega is equal to y of j omega by x of j omega, but x of j omega has got value 1. So h of j omega is equal to y of j omega. So it is the same as this thing, j omega plus 2 by j omega plus 1 into j omega plus 3. And we will just solve it by using the partial fraction. That is a1 by j omega plus 1 plus a2 by j omega plus 3. We'll cross multiply it. That is a1 into j omega plus 3 plus a2 into j omega plus 1. And we will give the value minus 3 to j omega so that this term gets cancelled. Here also minus 3 is given j omega. And we will solve for a2. We get a2 as 1 by 2. Similarly, on giving j omega is equal to minus 1, we will solve for a1 by using the partial fraction method. And the next step, we will substitute for a1 and a2. Half is taken outside because we have got both a1 and a2 as half. So half is taken outside. And on taking the inverse Ctft, you will get half into 1 by j omega plus 1. The Ctft is e raised to minus t. And 1 by j omega plus 3, the Ctft is e raised to minus 3t into u of t. So this is how you find the impulse response. Okay. Actually, this is your y of t is equal to, that is your h of t. Okay. Y of j omega is equal to h of j omega. Hence, you got the y of t. Hence, y of t is equal to h of t, you have to write, because h of t is the required impulse response. Okay. That is all for this problem. If you are asked to find the impulse response, just find y of t. That is equivalent to h of t, you can write. Hence, impulse response is equal to half e raised to minus t plus e raised to minus 3t u of t. Okay. Hope this problem is clear for you. Now let's move on to another category of problem that might be asked in this kind of section. Here also, the input and output of a causal LTI system is given by the differential equation d square y of t by dt square plus 5 into dy of t by dt plus 6 into y of t is equal to x of t. Find the impulse response of the system. That is in the same way we have done for the last question also. But here another one more subsection is given. What is the response if x of t is equal to e raised to minus 4t u of t? Here another input is also given. Impulse response means the input is delta of t. Plus you are asked to find out the response when the input is given. When some given known input is given. Okay, x of t is equal to e raised to minus 4t u of t. So you will proceed in the same way. That is, we will take Fourier transform on both the sides of the differential equation. Here it is d square y of t by dt square. So this is j omega square y of j omega. This is 5 into j omega into y of omega. This is just 6 into y of omega is equal to x of omega. Taking Ctft, you will get it in that form. Okay. So that is being written here, j omega square plus 5 into j of omega plus 6. You take the y of j omega whole outside is equal to x of j omega. Taking the transfer function, you get h of j omega is equal to phi of j omega by x of j omega. So we'll just rearrange, and it is of the form 1 by j omega square plus 5 j omega plus 6, which is factorized as 1 by j omega plus 3 into j omega plus 2. Hence we get a1 by j omega plus 3 plus a2 by j omega plus 2 is equal to 1 by j omega plus 3 into j omega plus 2. Partial fraction method, simple method. And we'll just cross multiply. That is a1 into j omega plus 2 plus a2 into j omega plus 3 is equal to 1. We will solve the value for a1 and a2. All the steps are similar that we have done in the last section. That is giving j omega is equal to, we can give minus 2 and minus 3. So that you can find out a2 and a1. a2 we got it as 1 and a1 we got it as minus 1. Hence h of j omega. That is, we will substitute in this equation. H of j omega can be written as a1 and a2 if you are substituting. You will get it of the form 1 by j omega plus 2 minus 1 by j omega plus 3. So this is your h of j omega. Just taking the impulse response, we will get what? We will get the, just taking the inverse Fourier transform, we will get the impulse response as 1 by j omega plus 2, it is e raised to minus 2t of t, and minus 1 by j omega plus 3, it is minus e raised to minus 3t u of t. Okay, so that is all about the impulse response. Now, impulse response is again written. That is the same answer as just rewritten. E raised to minus 2t of t minus e raised to minus 3t u of t. That is your impulse response. Okay. So in the next step, what you are going to find out is you're given with another input. That is x of t is equal to e raised to minus 4t of t. So you have to find out x of j omega for that. That is the Ctft for that, which is 1 by j omega plus 4. And we know h of j omega is equal to y of j omega by x of j omega. You want to find the output. That is, you have to find out first y of j omega. Y of j omega is what? H of j omega into x of j omega. So h of j omega we already know. So on multiplying, we'll get it of this form. Because h of j omega is already what? You already know it. X of j omega is 1 by j omega plus 4. The other two terms, that is 1 by j omega plus 3 into j omega plus 2. This actually constitutes the h of j omega. So here you have got three terms. Hence, we'll do the partial fraction again. So that a by j omega plus 4, b by j omega plus 3 plus c by j omega plus 2. Okay. So that is being equated to this particular RHS. That is 1 by j omega plus 4 into j omega plus 3 into j omega plus 2. We will solve for a, b and c. That is a into j omega plus 3 into j omega plus 2 plus b into j omega plus 4 into j omega plus 2 plus c into j omega plus 3 into j omega plus 4 is equal to, you have to solve. Okay, for a, b and c, putting j omega is equal to minus 3, j omega is equal to minus 2 and j omega is equal to minus 4. We solve it as b is equal to minus 1, c is equal to half and a is equal to half, which will be substituted in the equation of y of j omega. We get it of this one. Half by j omega plus 4 minus 1 by j omega plus 3 plus half by j omega plus 2. Hence, on finding the inverse Fourier transform of this particular equation, we will find the inverse Fourier transform. IFT means its inverse Fourier transform of y of j omega. We will get this of the form half into 1 by j omega plus 4, it is e raised to minus 4t minus e raised to minus 3t plus half into e raised to minus 2t. This is actually 2t u of t. Okay. So that is the final answer. So that's all. Now you can do this particular question as a tutorial question. D square y of t by dt square plus 2 into y of dy of t by dt plus 2 into y of t is equal to x of t. Find the impulse response using Fourier transform and inverse Fourier transform. It's the same way. You can just try this out also. Okay. That's all. Hope you find this video useful. Thank you. That's all.